Monday morning, January 26, 2026. And if you are listening to this live or even just snagging the download a few hours after the drop, the digital ink is barely dry.
Barely. We are talking about something that happened while most of our listeners were probably asleep.
We are talking about a seismic shift, a ripple effect that started approximately, 9 or 10 hours ago? And honestly, for those of us who track the bleeding edge of theoretical computer science and AI architecture.
The origin point is the first shock.
Exactly. The origin point of this ripple is as shocking as the content itself. It didn't come from the Bay Area. It didn't come from Shenzhen.
Not MIT, not DeepMind.
It originated in Tunisia.
It's remarkably rare that we get to witness the exact moment the pebble hits the water. Usually in our line of work, we're analyzing the waves months or, even years later.
After the peer review cycle has scrubbed everything clean and made it palatable.
Right. But today, we're standing right at the impact point. The water is still splashing all over us.
It really is. So here's the timeline. At 06.00 UTC plus 1, and then again precisely at 06.01, 2 papers were released. They just dropped onto the public preprint servers.
Simultaneously, which is a key detail.
A huge detail. And if you just glanced at the RSS feed, you might have thought, okay, these are 2 completely different disciplines. I mean, completely.
You'd see the titles and assume it was a glitch, or 2 different authors with similar names.
Right. One paper is tackling the absolute Everest of computer science. The P versus NP problem. The other is proposing a radical structural overhaul of artificial general intelligence using Arabic linguistic morphology.
On the surface, they look like they belong in different departments. One is pure complexity theory, the physics of computation.
Right.
The other is, it's computational linguistics and cognitive architecture.
But, and this is why we're doing this deep dive today, they aren't distinct.
Not at all. If you read them back to back, as we have spent the last 8 hours doing, fueled by a lot of coffee,
A heroic amount of coffee.
you realize they are the same argument. They are the same philosophical blade, just cutting through 2 different fabrics of reality.
And that is our mission for this deep dive. I want to be clear right off the bat.
Yeah.
We are not doing the Introduction to AI hour today.
Yeah, no.
We're not doing Turing Machines 101. If you're listening to this, we assume you know what P and NP are. You know the halting problem. You understand the stochastic, probabilistic nature of current LLMs.
We're skipping the basics because we have to. The material demands it.
We need to go straight into the deep end to unpack how these 2 papers, released 1 minute apart by a single unexpected author, might have just redrawn the boundaries of what we consider solvable and meaningful.
We have a massive amount of ground to cover. I think we need to structure this rigorously.
Agreed.
So here's the plan. We need to spend a good third of our time on the man behind the papers, Saif Mathouthi, because his specific position in the world, his outsider status, is actually critical to his methodology.
Okay, that makes sense. The who is part of the what.
Then, maybe the second third, we have to tear apart his argument that P versus NT isn't a math problem at all, but a physics problem.
And that's the one that will make the mathematicians either furious or ecstatic.
And finally, we have to look at his proposal that the future of AGI isn't in English-centric statistical guessing, but in the rigid generative. Well, he basically calls it an algebra of Arabic morphology.
All right, let's start with the source, the enigma. The name on the headers is Saif Mathouthi.
Right. And for those of you currently scrambling to check your citation managers or searching the faculty directories of MIT, Stanford, or ETH Zurich, stop.
Yeah, save yourself the trouble.
You won't find him there.
That is the first thing that smacks you in the face. Who is Saif Mathouthi?
Here's what we know, and it's not much. He's 35 years old. He is based in Tunisia, and most critically for how these papers are going to be received by the establishment, he is listed as an independent researcher.
Which is the polite academic way of saying he's an outsider.
He has no formal institutional affiliation listed. There is no university logo in the header, no grant number from the NSF or the ERC. He is, for all intents and purposes, a ghost.
In our ecosystem, that usually signals a crank. We've all seen the guys emailing proofs of the Riemann hypothesis written in, crayon.
Or they claim they've solved cold fusion in their bathtub. It's a very specific genre of scientific literature.
It is. But when you actually read Mathouthi's work, the crank alarm doesn't go off. Not for a second. This is incredibly dense, rigorous structural analysis. The formalism is impeccable.
It is, and I would argue that his lack of formal institutional education, or at least his lack of current institutional capture, is actually the key here. It has to be.
How so?
We are looking at the patent clerk archetype.
You're invoking Einstein. That's a heavy comparison.
I am, and I want to be careful. I'm not trying to hyperbolize the quality of the work before it's been properly vetted by the community, but I am trying to describe the position of the author. If we look back at the history of genuine paradigm shifts, Copernicus, Einstein, Wegener, with continental drift, they rarely come from the people sitting comfortably at the center of the discipline.
The high priests of the current paradigm.
Exactly. When you're deep inside the academy, you're trained to defend the current axioms. You spend your entire career solving puzzles using the tools the giants gave you. Your success depends on it.
You don't question the hammer, you just look for nails.
Precisely. Mathouthi, by virtue of being an independent researcher in Tunisia, is not beholden to the curriculum. He isn't worried about his index or pleasing a thesis advisor or getting tenure.
He's not playing the game.
He's not. So he's free to look at the tools themselves, the very definitions of time and meaning, and ask if the tools are broken. That's a question you can't really ask when your whole career is built on using those tools.
That outsider status allows for a specific kind of pattern recognition, doesn't it? If you are a specialist in complexity theory, you rarely talk to the computational linguists.
You might as well be in different buildings on opposite sides of campus.
Right. If you're a linguist, you rarely worry about thermodynamics or entropy. But because Mathouthi is outside those silos, he's clearly ignoring the walls between them. He's seeing connections that a specialist is trained not to see.
He is a cross-pollinator. He's a generalist in an age of hyper-specialization. And his methodology, which he explicitly outlines in the preamble of the first paper, is what ties this all together. He calls it applied terminological deconstruction.
This sounded a bit like, continental philosophy when I first read the abstract, a bit Derrida-esque. But it's actually very practical, almost like an engineering diagnostic.
It is. It's not postmodern fuzziness. It's a precision instrument.
Let's break down the triad he uses, because he applies this exact same lens to both the P vis-a-vis NP problem and the AGI problem. It's the skeleton key to his entire argument.
Right. So Mathouthi argues that anytime we use a high-level concept in science, whether it's time in a computer or meaning in a language, we're actually juggling three distinct entities simultaneously, often without realizing it.
Okay, what's the first one?
First, there is the symbol. This is the easy one. It's the formal definition. The variable t in the equation, or the string of code, or the word tree written on a page.
The literal thing you write down, the representation.
Exactly. The symbol is the map. Then second, there is the concept. This is the cognitive interpretation. It's what you think of when you see that symbol.
The mental model.
Precisely. You see T, and you think of a clock ticking, a flow of moments, a sequence of events. You see the word tree, and you picture leaves and bark and roots.
It's our human intuition, our baggage that we bring to the symbol.
That's a great way to put it, our cognitive baggage. And the third part of the triad,
the referent.
The referent, the operational reality, what is actually physically happening in the universe that the symbol is supposed to be pointing to.
So, for T in a computer.
It's electrons moving through silicon logic gates. It's a state change in a register. It's heat dissipating from the CPU. It's entropy increasing. It is a physical, irreversible process.
And his whole argument is that we have become sloppy. We've just collapsed these three things into one. We treat the symbol, the concept, and the referent as if they are interchangeable.
Constantly. He argues that the great stalemates of our time, like the 50-year deadlock in P vis-a-vis NP or the hallucination problem in AI, arise because we have allowed the concept to drift away from the referent.
We're manipulating symbols that no longer point to anything real.
Or worse, we're using a symbol that points to one referent in one context, physics, but we're applying our concept from another context, human experience. We're mixing and matching without realizing it.
He is essentially acting as a boundary cartographer. He's not solving the problem inside the map. He's redrawing the map itself to show where it no longer matches the territory.
That is a beautiful way to put it. He isn't trying to solve the math problem with more math. He's trying to show that the math has become detached from the physics. He's a philosophical auditor.
And this brings us to the timing. I mean, we have to talk about this. Why release these two papers at the exact same time? 0600 and 06.01, 9 hours ago. It's so deliberate.
It's a statement. It has to be. It's a power move, really. If he released the P versus NT paper alone, it would be pigeonholed. It would go straight to the theoretical CS departments.
And they would nitpick the notation for 6 months before even getting to the core idea.
Right. And if he released the Arabic AGI paper alone, it would end up in a linguistic journal or maybe an AI ethics journal, and the complexity theorists would never see it.
But by dropping them together.
By dropping them together, he is forcing us to see the meta pattern. He's forcing us to use his methodology. He's saying, don't look at these as two separate problems. Look at the tool I use to dissect them both.
It feels like a unified theory of information constraints.
It does. I think that's a perfect phrase for it. One paper deals with the limits of computation. How hard is it to know something? The other deals with the structure of meaning. How do we represent what we know?
And for Mathouthi, the answer to both lies in structure. In constraints.
In friction.
Constraints is the word that kept popping up in my notes over and over again. It's so countercultural to how we think about tech. It really is.
Yeah.
We usually think of constraints as negatives, right?
Mm.
Especially in Silicon Valley. We want unbounded potential, infinite scale, a frictionless experience. We want to eliminate all the barriers.
But Mathouthi seems to be saying that without constraints, without the limits of physics or the rules of grammar, you don't have reality. You don't have meaning, you just have noise, you have chaos.
It's like a sculptor. The art isn't in the clay. It's in the pieces of clay that are removed. The constraints create the form.
Exactly. And for an unknown researcher from North Africa to come out and tell the entire Western scientific establishment you are failing because you are ignoring the constraints of reality is, well, it's audaciously bold. It's a direct challenge.
It implies a worldview where physical reality is paramount. He is not a Platonist. He doesn't seem to believe that mathematical forms exist in some floaty, abstract ether.
No, he's an Aristotelian almost. He thinks if you can't build it with atoms or if you can't construct it with valid linguistic roots, it doesn't really exist in a meaningful way. It's just a fiction.
He is grounding us, forcibly. And I think we need to appreciate the risk he is taking here. By publishing independently, he is bypassing the gatekeepers, the peer reviewers, yes, but he's also bypassing the safety net.
Completely. There's no institution to back him up. If he's wrong, if there's a fatal flaw in his logic,
Sure.
His career is over before it even started. He'll be labeled a crank forever.
But he is betting everything on this triad methodology. He's betting that it's a strong enough tool to withstand the scrutiny.
Which I think is the perfect place to pivot. Let's apply this triad. Let's use his tool on his first major argument, the first paper, PVS-NP as a boundary phenomenon.
Okay, the 50-year deadlock.
The biggest beast in the jungle.
Just to frame the stakes here for anyone who might be a little rusty, Cook and Levin formulated this in the early 70s. It's one of the 7 Millennium Prize problems from the Clay Mathematics Institute.
$1 million bounty on its head.
$1 million? And, let's be honest, academic immortality.
Yeah.
But nobody has cracked it. We have had generations of the most brilliant minds in mathematics and computer science attacking this for half a century. And nothing.
And Mathouthi's thesis is that the reason nobody has solved it isn't because we aren't smart enough. It isn't a lack of mathematical ingenuity.
He says it's because the question itself contains a hidden flaw. He calls it an epistemic ambiguity.
And that ambiguity is all about the word time.
Back to the triad.
Right back to the triad. He argues there's a fundamental disconnect between time as a symbol in the math and time as a referent in the universe. To clarify this, he sets up these two domains, domain F and domain P. This is the absolute core of his first paper.
Let's define those very clearly because everything that follows hinges on this distinction. So domain F.
Domain F is the formal computational domain.
Okay, what does that mean?
It's the world of the Turing machine on a blackboard. It is the world of the textbook. In domain F, time is just a step counter. Step 1, step 2, step 3. It's a symbol. It costs nothing. It's an abstraction.
A pure abstraction. It produces no heat. It is perfectly reversible. In domain F, you can wait 1 trillion years for your algorithm to finish, and the abstract machine doesn't rust or run out of power.
Okay, so that's the idealized world of pure math. What's domain P?
Domain P is the physical computational domain. This is the laptop sitting in front of you.
Yeah.
This is the server farm in the desert humming away. This is your brain processing information.
The real world.
The real, messy physical world.
Yeah.
In this domain, computation is a material process. It is constrained by causality. It is constrained by the speed of light, by signal propagation delays between transistors.
And most importantly,
And most importantly, it is constrained by entropy. the second law of thermodynamics. You cannot flip a bit without a physical consequence.
He brings up Landauer's principle.
He drags Landauer's principle, which is usually tucked away in the physics of computation, right into the center of mainstream complexity theory. Landauer's principle states there is a minimum possible amount of energy required to erase one bit of information. So every logical operation has a physical cost. It generates a tiny puff of heat. It increases the entropy of the universe. You can't escape it.
You can't escape it. And Mathouthi's core argument is that we, as humans, tacitly import our intuitions from the physical world, from domain P, into the abstract world of domain F. And that's the mistake.
So when we read about an algorithm that runs in polynomial time,
in domain F, in the math, that just means its runtime growth fits a certain curve on a graph, n squared, n cubed. It's just a symbolic classification.
but in our heads.
In our heads, in domain P, we interpret polynomial as feasible. We think, oh, that's one of the easy ones. We can actually do that. It's efficient. And we interpret exponential as impossible.
Mathouthi says that's a trap. We're confusing the map with the territory again.
It is a semantic blur, a critical one. And he uses this to deconstruct the core asymmetry of P versus NP, which is verification versus discovery.
This is the crux of it, right? The classic example is the Sudoku puzzle. It is incredibly easy to check if a filled-out grid is correct. That's verification. That's P.
You just go row by row, column by column. It's trivial.
But it is incredibly hard, or can be, to solve the blank grid from scratch. That's discovery. That's NP.
Right. And usually we try to explain that difficulty mathematically. We talk about the size of the search space, the combinatorial explosion. We count the abstract steps.
But that's a domain F explanation.
That's a domain F explanation. Mathouthi argues that the asymmetry is fundamentally physical. It's thermodynamic.
Okay, walk me through that. How is solving a Sudoku puzzle about thermodynamics?
Think about it in terms of energy. Verification is checking a single given path. Someone hands you the completed puzzle. You just walk down one road and check the destination. Yep, this is correct. The energy cost is linear. It's a low entropy operation.
But discovery, finding the solution yourself.
Discovery is searching a vast space. You have to explore a million dead-end roads. You have to try a number, see it doesn't work, backtrack, erase it, and try another.
Every one of those erase operations.
Every one of those erase operations, according to Landauer's principle, has an irreducible physical cost. It generates entropy. In domain F, backtracking is free. It's just a step. But in domain P, it costs energy. You are fighting against the chaos of the universe to find the one correct, ordered solution.
So he's saying that searching a space costs real physical energy in a way that just checking a pre-existing path does not. And this physical entropic difference is the real reason P does not equal NP.
That's the heart of the argument. He argues that in domain P, the real world where we actually run our computers searching a large state space entails irreducible physical costs. You cannot get something for nothing. You cannot reverse entropy for free.
So the hardness of NP problems isn't just a clever math quirk. It's a physical barrier. It's a law of nature, like gravity.
That is what he is proposing. It just blows my mind a little bit. Because it implies that the reason we all feel PNP is true, the reason our deep-seated intuition screams these problems are fundamentally hard, is because our intuition is trained by living in a universe with entropy.
We are physical beings. Our brains are physical computers. We know, instinctively, that searching for a needle in a haystack is hard work.
Correct. Our intuition is trained on domain P physics. But the formal mathematics of P vs NP lives in domain F, where entropy doesn't exist. There's no concept of energy cost. And that's the disconnect.
And this is why he brings in the title of the paper. This is the boundary phenomena.
This is his grand conclusion. P vs NP isn't just a math problem. It isn't just a physics problem. It sits right on the jagged, fuzzy edge between formal computability and physical realizability. It's a glitch in the matrix where our definitions from two different domains improperly overlap.
So, let me see if I have this straight. The reason it feels true that P is not equal to NP is because our physical reality, domain P, imposes entropic costs on searching.
Yes.
But the reason it's so hard to prove mathematically is because our mathematical tools, domain F, have no concept of entropy.
You got it. We're trying to prove a physical law using a language that is blind to the relevant physics.
But then why does PMP even feel conceivable to some people? I mean, there are very smart, respectable computer scientists who think we might just find a clever shortcut someday.
And Mathouthi has an answer for that. He argues that happens when we use idealized models that strip away even more physical reality. If you imagine a computer with unbounded parallelism.
Like a hypothetical quantum computer that works perfectly with zero noise and infinite qubits.
Or a classical oracle machine, which is a theoretical box that can solve an NP problem in a single time step. A magic box.
But those machines exist only in domain F. They are mathematical fictions.
Exactly. They are mathematically admissible but physically impossible. They suspend causality. They suspend entropy. So his point is, the more you abstract away from physical reality, the more plausible PNP becomes. The closer you get to the real, messy physics of computation, the more impossible it becomes.
So the 50-year stalemate isn't a failure of ingenuity. It's a built-in structural tension. We're trying to prove that you can't build a perpetual motion machine. But we're forced to use a system of geometry that explicitly allows for perpetual motion.
It's an elegant explanation for why 50 years of brilliant minds haven't cracked it. They're not failing. They've been given a broken tool. They've been asked an ill-posed question.
Wow. Okay. Let's talk about the implications. Because if he's right, this isn't just an academic curiosity. This changes things. Let's start with cryptography.
Huge. Absolutely huge. The entire foundation of modern digital security, RSA encryption, elliptic curve cryptography, everything that protects your bank account and your messages relies on the assumption that certain problems, like factoring large numbers, are hard.
That they're in NP but not NP.
And there's always been this lingering fear that some genius in a basement is going to find a clever polynomial time algorithm for factoring, and the whole house of cards will come crashing down.
But Mathouthi is saying that hardness isn't just a math trick that someone might solve tomorrow.
He's saying it's grounded in the structural properties of physical computation. To break modern encryption isn't just about being clever. It's about being able to afford the astronomical energy bill. To break the code, you have to fight the universe's tendency towards disorder.
That actually makes me feel safer. It's not just that we haven't found the clever math trick yet. It's that the universe itself makes it physically expensive to run that trick.
It redefines security. Security isn't just about mathematical impossibility. It's about thermodynamic infeasibility. The cost in energy and time to break the code is designed to be larger than the resources available in the known universe.
Okay, what about the other big implication? The superintelligence angle. This ties directly into all the singularity fears.
It does. It directly confronts the fear that an AI will suddenly solve P, NTPN, and become a god, optimizing everything instantly. You know, the foam scenario, the hard takeoff, where it recursively self-improves into omnipotence in a matter of hours.
Mathouthi debunks that, or at least puts a very hard cap on it.
He calls it magic optimization. He says it's a fantasy born from domain F thinking. If computation is fundamentally physical, then any AI, no matter how smart, no matter how recursive, is bound by the laws of domain P.
It can't just think its way out of entropy.
It cannot calculate faster than the causal limits of its own hardware. That it can't perform an operation without paying the energy tax. It can't escape the second law of thermodynamics.
So no magic singularity where the AI solves the protein folding problem, the climate crisis, and the Riemann hypothesis in a nanosecond because it found a magical PNP algorithm.
Not unless that AI can fundamentally rewrite the laws of thermodynamics, which, according to this paper, it can't. The hardware, the atoms, the energy, the heat dissipation will always exact its toll. The universe will always put the brakes on.
That is a comforting, yet also a very sobering thought. It grounds us. It reminds us that we are creatures of matter, not just pure logic. We live in domain P.
And that grounding in matter and structure is the perfect bridge to the second paper. Because if P versus NP is about the fundamental structure of computation, the hardware of reality, the second paper is about the fundamental structure of meaning, the software of intelligence.
Let's pivot to that. The second paper, released at 06.01 UTC+1, is titled Linguistic Mathematical Modeling in the Structure of AGI.
And this is where things get really interesting and maybe a little controversial for the AI developers listening to us right now.
We all know the crisis. We have these amazing large language models, GPT-6, Claude 7, whatever the latest version is we're on now.
Yeah.
But they all have the same fundamental flaw. They hallucinate.
They make things up. They drift. They confidently state falsehoods. They lack grounding.
And usually we in the industry treat hallucinations like a bug. Like, oh, we just need more data, or we need to fine-tune the weights a bit more, or we need better reinforcement learning from human feedback.
We treat it as a software patch problem. But Mathouthi disagrees fundamentally. He diagnoses it not as a bug, but as a structural challenge. He says you cannot fix this with more data. That's like trying to fix a cracked foundation by adding more paint.
He goes right back to his triad: the symbol, the concept, the referent.
Right back to it. He argues that in current LLMs, which are at their core statistical models, there is an inherent dissociation between the three. The model is designed to predict the next most probable word, the symbol.
It's a sophisticated autocomplete.
An incredibly sophisticated autocomplete. It calculates the most likely token to follow a sequence of other tokens. But it has no mechanism to verify the concept or check against the referent. It is just guessing the context based on trillions of examples from the internet.
It's like a parrot that has read every book in the library. It knows which words sound good together, it knows the rhythm and pattern of a sentence, but it doesn't actually know what the words mean in reality.
Precisely. It mimics context brilliantly, but it does not understand semantics. Mathouthi calls this the impasse of statistical modeling. It is a probabilistic approximation of meaning, not meaning itself.
And his proposition is radical. He says we need to move from statistical modeling to what he calls systematic semantic modeling.
We need to build AIs on a system that has, quote, internal generative regularity.
And here is the curveball, the thing that probably made people spit out their coffee this morning. He proposes the Arabic language as the blueprint for this new model.
Now, before anyone gets defensive, and the paper is very, very clear on this, he repeats it several times, this is not about cultural superiority. This isn't about nationalism or religion. He's not saying AI needs to speak Arabic to be smart.
He's very explicit. He calls Arabic a structural laboratory.
Yes. That's the key phrase. He treats Arabic not just as a cultural language, but as a piece of legacy software engineering that has been stress-tested and debugged for nearly 2,000 years.
And he breaks it down using an analogy that any software engineer listening will immediately understand. He uses object-oriented programming terms. And when you look at it through that lens, it is startlingly modern.
It really is. I found this section of the paper just breathtaking.
Let's walk through the analogy in detail. He starts with the Arabic root, the G-dir.
In Arabic, almost every word can be traced back to a root, which is usually 3 consonantal letters. Mathouthi equates the root to an abstract class in programming.
Okay, so what's an abstract class?
It's like a blueprint. It contains the core semantic DNA, the essential properties and methods, but you can't create an instance of it directly. It's a pure concept.
So, for example, he uses the root KTB. It doesn't mean a specific word yet, but it carries the abstract concept of, what? Writing or marking.
Exactly. The semantic field of to-write, that's the abstract class. It defines the boundaries of the meaning. Then you have the pattern or the template, the wazn. These are the vowels and sometimes extra letters that you weave into the root.
And he equates these to
generative functions, or class constructors, if you like. They are operations you perform on the abstract class.
And when you run the root through the pattern, when you apply the function to the class,
you get the word, the semantic object, a concrete instance. So if you take the abstract root KTB and apply the pattern for doer, which is file, you get katib,
a writer.
A writer. If you take the same root and apply the pattern for the thing which is done, mafal, you get maktub.
Something written like a letter.
If you apply the pattern for place, mafal, you get maktab.
An office or a desk, the place of writing.
And if you apply the pattern for instrument, mafal, you get maktab.
A typewriter, or now maybe a keyboard. An instrument of writing.
Do you see the logic? The key here is predictability. It's systematic.
It's algorithmic. It's not random.
Exactly. It is a generative regularity. Now, contrast this with English, which is what current LLMs are primarily trained on. English is an analytic language.
What does that mean?
It means it relies on cumulative context. Word order and helper words create meaning. If I give you the English words write, place, and tool, you have to string them together. The tool is in the place for writing. The meaning is distributed across the whole sentence.
The relationships are external to the words themselves.
Yes, and it's often ambiguous. If I say the word writer, you know what it means. But what about right place or right tool? It's not immediately clear. The system is just guessing based on proximity and statistics.
Whereas Arabic, according to Mathouthi, carries predictive semantic properties within the word structure itself.
Correct. The word itself contains the coordinates of its meaning. The root tells you the what, the semantic field, and the pattern tells you the how, the role it plays. You don't need the rest of the sentence to know that maktab is a place associated with writing. The internal structure tells you.
And this brings us back to solving hallucination. How does this beautiful logical structure actually stop an AI from lying or making things up?
Validation. This is the holy grail of AGI safety. Currently, LLMs have no internal way to check their own work. They just output the next most likely token and hope for the best.
They can't self-correct on a semantic level.
But if an AI is built on this root pattern logic, it imposes a validation mechanism at the most fundamental level.
So if the system tries to generate a word, it has to perform a check first.
Exactly. It would have to ask, does this root exist in my lexicon? Is this pattern a valid morphological template? Does this pattern logically apply to the semantic field of this root? It can't just generate a word because it sounds good or has a high probability score in a specific context.
The word has to fit the generative logic of the root system.
Precisely. If the AI tries to use the root KTB in a pattern that implies, say, drinking, the system would throw a fatal error. It's a compile time error for meaning. The operation is semantically invalid.
So if the system tries to generate a word that disconnects the symbol from the concept, the structural constraints of the language model itself would flag it as incoherent.
Ideally, yes. It acts as a powerful constraint against semantic drift. The system can reject a sentence not because it's statistically unlikely based on its training data, but because it is semantically incoherent based on its own internal generative rules.
It's building a guardrail, a safety check into the atomic structure of the language itself.
Which is something current LLMs desperately, desperately lack. They are fluid, slippery, associative, and hallucination-prone. Mathouthi wants to inject rigidity, a constructive, logical rigidity, into the core of the system.
This leads to his other point about this structure, which he calls a temporal reference.
Yes, and this connects back to the idea of stability over time. A true AGI can't be ephemeral. It can't just chase the latest slang or have its understanding of reality drift with every new batch of training data from the internet.
It needs a stable core.
And he mentions that the core morphology of Arabic has remained remarkably stable over very long periods.
Right, he makes the point that a text from 1,000 years ago, in Arabic, like from Ibn Khaldun or Al-Ghazali, is much more comprehensible to a modern, educated speaker than a text from 1,000 years ago in English, like Beowulf is to us.
Which is almost a foreign language. The grammar, the vocabulary, it's completely different. But the Arabic root and pattern system is a foundational constant. Mathouthi argues that an AGI needs this foundational stability to operate across different times and contexts without needing constant external recalibration.
It needs an internal anchor to prevent it from just becoming a mirror of the noisy, ever-changing present.
Internal generative regularity. That's his key phrase. It needs to generate meaning from the inside out, using a stable set of rules, not just mirror the statistical chaos of the outside world.
And again, just to be absolutely clear and to reiterate what he says in the paper, he clarifies this isn't about making the AI recite pre-Islamic poetry or become a theologian.
Not at all. It's about the logic, the architecture.
It's a structural laboratory. He's inviting computer scientists to look at Arabic morphology not as a linguistic curiosity for area studies departments, but as a formal system, a data set of logical constraints that have successfully grounded meaning for millennia.
He's saying, look, here is a natural code that has elegantly solved the symbol grounding problem. It rigorously separates the abstract class from the instance. It has built-in validation. Let's copy its architecture.
It is absolutely fascinating.
Yeah.
He is essentially saying that English, with its chaotic, loanword-heavy, structurally loose, and context-dependent nature, might be the wrong substrate for building a truly grounded AGI.
Or at least that building AGI by applying purely statistical modeling to a vast corpus of English text is a dead end for achieving true understanding. We're building these incredible skyscrapers on a statistical swamp. Mathouthi is suggesting we need to find bedrock.
Okay, so let's take a breath and try to bring this all together. We have these two dense, paradigm-shifting papers. One says computation is bound by the bedrock of physics, what he calls domain P. The other says intelligence requires the bedrock of linguistic structure, like Arabic morphology.
The unifying theme is unmistakable. It's the word we keep coming back to. Constraints.
Constraints are not the enemy. Constraints are necessary for reality and for meaning.
In paper 1, he says you cannot compute without paying the tax of entropy. You are constrained by domain P. If you ignore that, you get mathematical paradoxes.
And in paper 2, he says you cannot generate meaning without paying the tax of morphology. You are constrained by the root and the pattern. If you ignore that, you get AI hallucinations.
And the entire tech world, the entire ethos of Silicon Valley is obsessed with frictionless everything. Infinite scale, unbounded AI, move fast and break things.
And Saif Mathouthi is standing in Tunisia holding up a stop sign and saying, friction is reality, the constraints are the whole point.
If you remove the friction, you leave reality. You enter the world of hallucinations, of magic optimization, of mathematical fictions that can't be built.
It is a profoundly conservative argument. And I don't mean that in a political sense. I mean it in a philosophical conservationist sense. His entire project is about conserving the connection between the symbol and the real.
And it challenges the global intellectual hierarchy in a way that is, frankly, hard to ignore. It's uncomfortable.
Let's go back to the author for a moment to close the loop. 35 years old. Based in Tunisia, no institutional backing, no PhD supervisor telling him what to write.
And this brings us right back to the start. Why does the origin of this matter so much? Because if he is right, if even 10% of this is right, it means we have been looking for the answers in all the wrong places.
We have been looking at the center, at the big labs, at Google and Meta, at the established Ivy League theories. We look at the people with the biggest grants and the most citations.
And maybe we should have been looking at the boundaries, at the margins.
The boundaries between math and physics.
The boundaries between language and code.
The boundaries between the global north and the global south.
Mathouthi is that boundary cartographer. He is showing us that the most interesting, most fruitful discoveries happen where the disciplines collide and grind against each other. He's showing us that you can't understand computation without physics, and you can't understand intelligence without structure.
It really makes you wonder what else we are missing. What other foundational assumptions are we clinging to?
That is the final provocative question he leaves us with, isn't it? If we have been blind to the physics in our math and blind to the structure in our AI, what other boundaries are we failing to see right now? What other 50-year deadlocks are just epistemic ambiguities waiting for someone to deconstruct them?
What other fundamental assumptions are we making just because they make the math easier?
Or because they fit our particular cultural or linguistic intuition? We assume time is a simple abstract line. We assume meaning can be found in statistical correlations. Mathouthi questions both, from the outside.
It is a Monday morning in 2026, and the world feels slightly different than it did yesterday when we woke up. The problems we thought were impossible might just be badly framed.
The map has changed. We just need to learn how to read the new one. And maybe we need to be more willing to read maps drawn by people we didn't expect from places we weren't looking.
We will have the links to both papers. P versus NP is a boundary phenomenon, and linguistic mathematical modeling in the structure of AGI in the show notes. I cannot recommend highly enough that you read them. Don't just rely on our summary.
Please don't.
Read the applied terminological deconstruction section in the introduction for yourself. It is a tool set you can apply in your own work, whatever field you're in.
Absolutely. It's a masterclass in first principles thinking. Even if you end up disagreeing with his conclusions, the method itself is invaluable.
This has been the deep dive. We unpacked the impossible today.
Or at least we found a compelling new reason for why it was impossible.
Catch you on the next one. Keep thinking.